Today we are going to start our new topic, that is residues. In complex analysis, residues are much known by everyone, and in every completion exam it is asked to calculate residues of certain function. It is very useful because with the help of residues we can calculate the value of complex integrations also. So thus we can bypass the complex integration and get direct value of their integrations with the help of residues. That's why these are very important. So what are residues? Now we have studied about the expansion of complex function with various series expansion like low end series expansion and alt extra. So the coefficient of 1 upon z minus a, which is b1 and etc. Now in the expansion of function of z, around that isolated singular point is the residue of that function. Okay, so suppose we have singular point z equal to a and we expand the complex function. So the coefficient of 1 by z minus a is the residue. We know that low series expansion is a naught a on z minus a to z minus a square plus b1 by z minus a plus b2 upon z minus a square. Thus it goes on. So residue of function z of a is equal to always b1. Okay, remember, residue is always the coefficient of 1 by z minus a. So b1 will be the residue always. And how we will write it? So b1 is residues function of z equal to a will be equal to 1 upon 2 pi eta integration of that function. Like this. So with the help of this we can calculate the integration, complex integration. This is its usability. That's why it is very useful. So complex integration of any function will be equal to 2 pi iota. Okay, 2 pi iota and residue of that point, about that point of the function, which is 2 pi iota b1. So simply if we say what is residue, residue is simply coefficient of 1 by z minus a in the expansion of the function, which is generally called as b1. And why it is useful? Because the value of complex integration will be 2 pi iota times of residue. It is the bypass technique to solve the integration in complex analysis. Now we will study about residue theorem. Suppose we have z function and you know that it must be analytic about a point. Suppose this is analytic in a closed contour C and it is not analytic at a finite number of isolated singular points within C. So we have closed contour C and function is analytic, and for some point which is infinite number it is not analytic at some point. So the complex integration of function will be 2 pi iota times of residues around those finite points. Okay, b1 around za1, b1 around a1 plus b2 around a2, and thus it will go on. a1 a2 are the point about which function is not analytic. So what we are doing is, suppose it's a closed contour C and these are the points a1 and a2, and these points are not inside the closed contour. So at these points function is not analytic. So we will find out residues around these points, and when we multiply some of these residues and multiply it with 2 pi iota, we will get the integration of complex function. Like if we have the function e raised to the power 1 by z, so you know expansion of e raised to the power x. What is the expansion? 1 plus x square upon factorial 2 plus x cube upon factorial 3, like this. So 1 plus x, 1 plus x plus x square upon factorial 2. So 1 plus x plus x square upon factorial 2 plus x cube upon factorial 3, and it will goes on. So about z equal to 0, you can see it is not analytic. So it's an isolated essential singularity of e raised to the power 1 by z. Okay, it is isolated and essential singularity of e raised to the power by z. Suppose we have another function. You can see z equal to 0, z is equal to 2 are the singular points. Both are the isolated singular points. Now you can see z equal to 0 is the pole of order 1 and z equal to 2 is the pole of order 5th. Now why we are taking 5th order and not taking order 2? Because in order to define its limit we need to do z minus 2 raised to the power 5 and it will be cancelled out the denominator. So in order to find limit we will use z minus 2 raised to the power 5. That's why to becoming existence of the limit of that function we need 5th order pole. That's why the z minus 2 is the 5th order pole. I already explained it here like this. Limit is 10 to a z minus a raised to the power m. F of z is finite, so limit is finite with the help of order m. So this will be the order of the pole, like here. Now you get it. Okay, suppose we have a function z equal to 0. So z equal to 0 is the isolated and essential singular points. Now we have a question here, so just solve it. So when we are doing limit z tends to 0, z minus sin z by z square, so you can see 0 0 0, so it's 0 by 0 form. So we will apply L'Hospital rule. What will z differentiation of z1 sin ka cos z and z square will be 2z. It again comes 0 by 0 form, so again differentiate cos minus sin minus minus plus sin z and 2 will be in denominator. Now just sin z by z will be 0. Here also if you take 1 upon z square out, then z minus and sin z expansion of sin z x minus x cube by factorial 3 plus 5 upon factorial 5, so on. So when you put limit z tends to 0, what will happen? This will be cancelled out and it will be left out. So limit z tends to 0, here also z and whole z will be there, so it is giving 0. So it is giving 0 means it is giving finite value. So z equal to 0 is removable singular point. Now we have another function z plus 1 sin 1 upon z minus z 2. So z equal to 2 you can see is an isolated and essential singular point. Now how you will solve it, how you can get the limit of that functions. So you can solve it directly also, but we are using here a variable t. So z minus 2 equal to t and z equal to t plus 2, put it in here. So function will be converted like this, and if you expand sin 1 by t is x minus x cube upon factorial 3 and so on. Now you can see this 1 by t is finite power, means here is b1 3 5 like this. So when you multiply this with t, what you will get? This will be cancelled. 1 plus 1 by t square 3 by, it will goes on like this. Means you have to multiply these both terms. So when you are multiplying t with this, you will getting 1, and when you are multiplying 3 with this, you will getting 3 by t. Again multiply 3 here, so you will get t square, and then we will multiply 3, you will get t cube. Okay, so you are left with this 2, with 3 and with t. Now you can clearly see, you can say that this is going up to infinity. So both this part and this part of the expansion of the function are having infinite power. This is not giving finite b1 or b2, so this is not essential singularity. So we can see z equal to 2 is isolated and non-essential singular point. Now this is another function. When you draw it, you get cos z and sin z, so tan z equal to 1, so it will be pi by 4. But when you do the function, you can see you will get so many pi by 4s. So it is 2n plus 1 pi by 4, it is pi by 4, 3 pi by 4, and so on. So 2n plus 1 pi by 4 will be value of the function. So z equals to an isolated singularity. And whenever you are applying a hospital rule, you must know that it is applicable only to condition, only with these two forms. A hospital rule cannot be applied everywhere. If it function is given with the limit 0 by 0 infinity, then only we can apply a hospital rule. Now, calculation of residues. There are three ways to calculate the residues of the function. And why we are calculating residues? Because we have to find the value of complex integration. Such we can bypass the complex integrations in very convenient way, and we have the values of those complex integration. Suppose we have a function and it is simple pole of order 1, and so residue of function at that point will be limit z tends to a z minus a and f of z. Okay, always remember, it is very important how you are calculating the value of the functions at that point. So just residue is function, residue is the limit of that function except that point, because z minus a will be cancelled out. Okay, in example you will see it clearly. This is the Lorentz expansion of the function. So when you multiply it with z minus a, z minus a will be cancelled out, so you will only have b1, and this is the residue. Let fz is second method. Fz is phi z and psi z. So you will, and psi z can be explained at z minus a coefficient of gz, and gn not equal to 0. So residues of function of z is at that point value of the phi and psi prime. So what you are doing here is you are taking first derivative of the denominator. Remember, here you are having first derivative of the denominator of the function. Now, if function of z has a pole of order n at z equal to a, now here was simple pole, and here is pole of order n, 2, 3, maybe 5, maybe n. So how you will calculate residue? 1 upon factorial n minus 1. And d n minus 1 upon z minus n, z minus a and f of z about that point. It is very easy. You will see in examples. Now, some standard integration by using residue theorem. Now, suppose we have a real integration in terms of cos theta and sin theta, and whole circle is there. So now, so how you will solve it? You simply put z equal to e raised to the power I to theta. What is it representing? Whenever you are taking z equal to e raised to the power I to theta, it is simply representing the circle of radius 1. You know cos theta is this and sin theta is this. So when you calculate d theta is e raised to the power I to theta times iota. So it will again convert it into iota z. So dz will be iota z d theta. Put those values in I and you will calculate the value. It will be solved out as z plus 1 by z upon 2, which will be converted to z plus 1 upon 2z, and it will be z square minus 1 upon 2z iota. Now, if you have the real integration in the forms of function of x, and limit is minus infinity to plus infinity, and function of x can be defined as px by qx. Now, if qx has no real zeros, means qx not 0, and having some degree which is greater than px, and denominator degree is greater than the numerator, so you will calculate the integration around semicircular organ plane like this. Simply it is the residue. Means you are taking here, see the closed contour around that semicircle. So you can put the limit as minus infinity to plus infinity. Again, suppose you have integration with sine and cos. So how will calculate? Simply forget this and convert it into e raised to the power iota m h 8. Because when you expand e raised to power theta, you will get cos theta plus iota sin theta. So after solving this part, the real part of this will give you the value of this integration. The imaginary part of this will give you value of sine integration with the function. And to calculate the full value, simply you just calculate residues v1 v2 and multiply it with 2 pi iota. You know this well. Okay, example we will be taking in our next class. Thank you.